Hi, good morning, everybody. Thank you for taking some time to attend our electromagnetic webinar. I'm excited to present this information to you, as it's been a solution that's been a long time coming, if you will. I've come across several opportunities over my career that would have been nice to have this in my back pocket, and now Dassault has finally given us that offering. For those of you that don't know me, I'm Rob Stoklosa. I'm with TPM. I'm out of the Raleigh, North Carolina office. And today we've got Jim Reed with us. TPM has partnered up with Optimal Designs, which is a Dassault partner. So Optimal is kind of handling the opportunities that come up regarding electromagnetic simulation and support, and Jim's kind of leading that charge. So we've got him on the call with us today, and I'll let him introduce himself. But as I said, I'm excited to be able to offer this. It hasn't been a solution in the past that I really had anything I could, or it hasn't been I haven't had a solution to address these types of challenges. Hopefully today you'll find, aerospace, high tech, medical, industrial, high power applications. These are typically where we find these types of opportunities. It is an electromagnetic solver, so that's something we haven't dealt with in the past. And with regards to that, this may initiate a different set of a team or different members of the of your company that we haven't spoke with in the past. So for those of you who are SolidWorks kind of tried and true SolidWorks people, please try to get in touch with whatever departments this may affect, as it hasn't been something that we've been able to offer in the past. So quick few things to look out for, and I'm sure Jim will touch on it. As with all Dassault products, the user friendliness of the interface, I think you're going to find very comforting. It has a very rich help menu, just like most of our applications today. So a little bit of, you can get some hand holding through some training, but we like for you to help yourself. And I think the help menu does have some pretty in-depth information in it that can help keep you going. And it is integrated for SolidWorks data. So for those of you, that do have models created on the platform or in SolidWorks, just know, one of the big takeaways is that seamless integration. So hopefully you find this beneficial. And again, I appreciate everyone's time. With that, I'll go ahead and pass it over to Jim Reed.
Thank you, Rob. Yeah, let's go ahead and start.
Welcome to the presentation on CST Studio Suite for electromagnetic simulation and SolidWorks integration, presented by Jim Reed of Optimal Designs. Content for today's presentation includes the following: presenter introduction, why electromagnetic simulation, value of electromagnetic simulation, integrated design tools, user-friendly interface, geometry, and CAD import, SolidWorks parametric integration to CST, CST Studio Suite solver overview, key technologies and industries, and summary of benefits. Optimal Designs is a CST Studio Suite service provider for Dassault systems in North America and Europe. We collaborate in the SolidWorks business channel for a full range of CST enablement services, including CAD integration, custom training courses, model library generation, and advanced ongoing technical support. Areas of expertise include coaxial and waveguide technologies, power divider and coupler networks, 2D, 3D filters, 2D, 3D antennas, and PCB design. For myself, I have over 25 years of experience supporting CST for aerospace, defense, telecommunication, and consumer electronic companies in the electromagnetic simulation design and software support. I was one of the first application engineers for CST North America from 2000 to 2004, and more recently, I've led the CST Studio Suite sales and support with several Dassault system partners from 2019 to present. My business partner in Europe is Radu Vonya, who supports our efforts in PCB simulation design. Why conduct electromagnetic simulation? Electromagnetics are all around us, from turning on the light, enjoying wireless home audio or gaming devices, touching the screen of our mobile device, utilizing the electric motor and electric bike or electric car, calling friends and family on a mobile phone, or receiving medical treatment, including an MRI. In the electromagnetic spectrum, we can see the range of frequencies and different types of devices in this image, including the very small fraction of visible light. The electromagnetic equations can be written in several forms, including static, low frequency, and high frequency. Historically, the commercial market provides a separate software solution for each mathematical form. This is what separates CST. In a single interface, the complete electromagnetic spectrum is represented, from DC to daylight, both in time domain and in frequency domain, and also includes multiphysics capability for thermal, fluid dynamics, and structural analysis. What is the value of electromagnetic simulation? Throughout this presentation, I will show you how CST Studio Suite can address challenges and provide you with state-of-the-art solver solutions. Areas include emerging markets, electrification, 5G and beyond, Internet of Things, smart objects, and autonomous driving. Design challenges. Miniaturization and component integration adds complexity, as well as new material sciences. Innovation. Enhanced understanding of the design space with field visualization. Virtual prototype, advanced prediction on performance, manufacturing tolerances, and thermal management. Compliance and compatibility, prediction of compliance issues, as well as compatibility issues with EMI and EMC studies. Multidisciplinary working environment, a cloud collaboration environment amongst engineers and project managers. Time to market and cost. Design cycle time is reduced, quicker to market, at a less cost. This is a snapshot of different EM applications moving from low frequency to high frequency. What defines a low frequency from high is the relative electrical size of the device in wavelengths. Low frequency devices are a fraction of a wavelength, where high frequency devices are multiple wavelengths. Starting with low frequency applications, examples include sensors, MRI, electric motors, and transformers. Moving over to high frequency, examples include antennas, filters, and waveguides. Electronic analysis in CST can cover both low frequency and high frequency, including low frequency power integrity analysis to high frequency, high speed transmission lines. And lastly, more exotic and EM applications include particle analysis for particle acceleration and tracking, as well as studying high power applications for corona effect and multipaction. A recurring technology example is antennas. And in this slide, we see a common mobile phone which operates with 6 different antennas. CST not only allows the design of a single antenna or array, but also the complete operating analysis of the phone and if an interference violation exists. Another technology example which is related to antennas is biomedical exposure. CST includes a library of biomedical models as well as post-processing templates for exposure analysis. Integrated design tools. CST has an array of integrated design tools, including antenna maggots for antenna design, filter designer for 2D or 3D filter design, FEST for waveguide network design, Spark 3D for corona and multipaction analysis, and ITEM for advanced spice creation from simulated S parameters. User-friendly interface, geometry, and CAD import. A new user will recognize immediately that CST's GUI is both advanced and friendly to use. It has a common Windows bar for navigation, on-screen parameter lists for easy access, progress and message windows, And lastly, a vertical navigation tree that quickly changes the primary user screen between pre and post-processing. The embedded help files are both expansive and easy to navigate, with hyperlinks to relevant material. You can find information ranging from mathematical explanation of solvers to resolving an operational question. The component library includes over 500 pre-built models and over 50 tutorials for step-by-step model creation. Although CAD integration will be discussed next, CST does include an advanced 3D modeler with standard primitives as well as sophisticated geometry commands. Some of these geometry commands include the loft, twist, spiral, and arbitrary 2D rotation. CST allows for seamless integration with a broad selection of CAD systems, including SOLIDWORKS, CATIA, STEP, OBD, and more. After importing a CAD model, the user can still make geometry operations to the objects, including removing unneeded features for EM analysis, as well as parametrizing planar or circular faces. SOLIDWORKS Parametric integration to CST. A key feature for CST is the live link feature to SOLIDWORKS. In this parameter import feature, CST can open a native SOLIDWORKS file with parameters, read these parameters, and make changes directly to the SOLIDWORKS file. This removes the need for importing and exporting with CAD engineers. Now CAD engineers and electrical engineers can collaborate from the same native file. This allows the CST engineer to conduct both parametric and optimization analysis using parameters built into the SOLIDWORKS file. This is a new paradigm, both in simplifying the number of steps for SOLIDWORKS engineers to collaborate with electrical engineers, but also reducing human error in the process. CST Studio Suite Solver Overview. CST includes 25 physics solvers broken down into different family groups, as well as a system and circuit simulation tool. We are going to conduct a deep dive to illustrate the broad solving capability and value. The base package of CST Studio Suite covers all these design modules, from static to high frequency, PCB simulation, multiphysics, as well as circuit simulation. Let's start off with the high frequency subset of solvers and flagship, Microwave Studio. Microwave Studio includes 7 high frequency solvers, including 2 general purpose solvers, the time domain and frequency domain, as well as more purpose specific solvers of eigenmode, integral, method of moments, and asymptotic. This slide conveys the mathematical technique and meshing type per solver. Depending on the solver, different meshing techniques are employed, ranging from non-uniform hexahedral mesh used in time domain, curved tetrahedral mesh used in frequency and eigenmode, and curved triangle mesh used in integral solvers. The 2 general solvers that utilize 3D volumetric meshing and provide S parameters are the time domain and frequency domain, where the time domain includes the default finite integration technique, but can be switched to the transmission line method for specific applications. The frequency domain solver is a standard finite element method approach using variable order curved tetrahedrons. Some key differences of the time domain and frequency domain are the following. Time domain is often associated with broadband transient simulation, where frequency domain uses a sequential frequency simulation approach. Time domain uses a time marching transient analysis, where frequency uses a frequency steady state analysis. Broadband S parameters are created in the time domain after a digital Fourier transform, where broadband results in the frequency domain utilize a frequency sweep. Time domain is known for solving electrically large structures compared to electrically small to medium with frequency. The meshing approach in time domain is very effective for complex imports, where the meshing approach in frequency domain is effective for high aspect ratio geometry. Time domain simulates broadband structures very quickly, where frequency domain simulates high Q structures very quickly. Time domain simulation time can be greatly enhanced with GPUs, up to 10x, where speed enhancement in the frequency domain depends upon multiple core CPUs. This graph shows the relationship of electrical volume and mesh size to a typical solve time in time domain and frequency domain, where the time domain traits include memory efficiency, scale is linear with mesh volume, but additional solve time is needed for high Q, high geometry aspect ratio, or large number of ports. In the frequency domain, it is more memory intensive. It has two different solving approaches. In the iterative solver, it uses less memory than the direct solver, and the iterative solver solves for one row of the S matrix per solution, much like the time domain. But it has another approach, the direct solver, which can complete a full S matrix in a single simulation. And here we can see the different curves for the direct, frequency domain, iterative, versus the time domain, which is much more linear. The other four solvers in the high frequency suite can be referred to as special purpose solvers. The integral and asymptotic are for electrically large structures. The eigenmode solver is used for studying 3D resonant structures or their eigenmodes. And the multilayer solver is a planar method of moment solver that can be very efficient for PCB simulations. Technology examples for high frequency include, but are not limited to, aerospace applications like EMI shielding and radar cross-section, component design like cavity filters, antenna design or wireless coupling, and PCB signal integrity analysis. Let's move on to EM Studio for static and low frequency. Static solvers mean no time varying fields, and these solvers include electrostatic, magnetostatic, and stationary current, where low frequency and time and frequency domain assume small changes to the fields in time. Key areas for static design include MRI and life sciences, and induced current losses and transformers. At the forefront of low-frequency design are electric motors, especially for the research in the automotive industry, as well as generator design for water or wind turbines. EM Studio also includes link solvers to another Dassault low-frequency product called Opera, which has advanced field-dependent magnetic properties. Now let's take a look at the most industry unique set of solvers, Particle Studio. Particle Studio includes four solvers: tracking solver for particle movement and static EM fields, wake field solver for particle mean excitation, particle and cell for transient particle movement, and electrostatic particle and cell for space charge versus time effects. Few people know that CST's origin by Professor Thomas Weiland was not to solve Maxwell's equations for wireless design, PCB, or motor design, but to assist in designing the world's most advanced particle accelerators. Particle Studio was the first CST production and is a unique set of solvers rarely found in the marketplace. Applications include electron gun and also magnetron design. Moving on to Multiphysics Studio. Multiphysics solvers include stationary and transient thermal solvers, conjugate heat transfer solver, and structural solver. Stationary thermal solver is a steady state analysis where applications include PCB heating distribution. Transient thermal solver is time-varying thermal analysis. Applications could include microwave heating. Conjugate heat transfer solver simulates heat transfer and fluid flow and includes conduction, convection, and radiation heat sources. And lastly, structural mechanics solver calculates stress, strains, deformation from mechanical load, or EM thermal deformations. The stationary and transient thermal solvers are very quick and accurate, assuming the correct approximation is made for the heat exchange boundary to air. But when a more complicated approach is needed, the conjugate heat transfer solver employs computational fluid dynamics to simulate thermal conduction, convection, and radiation simultaneously in the transient or steady state regime. And it can incorporate fluid flow cooling modules for both air and liquids. In this example, a forced air fan is being used in several configurations for a PCB design. Next, let's look at Cable Studio. Cable Studio allows the engineer to create or import complicated cable routing networks, which can be used in the automotive, naval, or commercial environments. There is a library of cable harnesses, transitions, and shielding options, and simulation results include S parameters and radiated emissions. Next, PCB Studio. PCB Studio incorporates 3 mathematical techniques, including 2D transmission line, 3D partial element equivalent circuit, and 3D finite element frequency domain. PCB Studio has a total of 5 solving tasks, and here we will discuss the high frequency analysis. SITD analyzes transmission line behavior while providing crucial time domain results, including delay, reflection, and over-undershoot, as well as crosstalk. SIFD analyzes the frequency domain S parameter results, and DDR4 analysis is a wizard that uses the SITD for specific results related to DDR4 memory technology. Moving on to other PCB Studio tasks, IR drop analysis uses the 3D PEEC solver to analyze voltage drop on a power or ground plane and can export these losses as a heat source for thermal management studies. PI analysis computes the impedance over a power distribution network and includes a topographical impedance display for quick analysis of problem areas. Geometry is imported into PCB Studio from an array of PCB layout tools, including Cadence, Mentor, and Altium, and also includes general file formats such as OBD++. Signal integrity results include S parameters or transient results like eye diagrams. Many PCBs have FCC requirements for radiated emissions, which can be computed in CST. This virtual prototype can save time and money before compliance testing. In this example, after the IR drop calculation, the 3D losses can be exported as a heat source for thermal and structural solver co-simulation. Board check. Board check is built inside of PCB Studio and allows for imported boards to be evaluated on industry standard netlist routing rules. This is a value add on design rules before time is invested in simulation. And lastly, Design Studio. Design Studio is a schematic design tool which uses SPICE format for system-level simulation and analytical and measured-based models. Customizable libraries of linear and nonlinear components, including IBIS models, and integration to 3D EM simulation projects. System assembly and modeling, also known as SAM, allows engineers to compare the results of different solvers or model configurations within one simulation project and perform post-processing automatically. SAM also allows for hybrid or multiple solver simulations. Examples include simulating a solo antenna in the frequency domain and allowing the antenna in the near field or far field as a source file in the integral and asymptotic solver, including antenna placement studies. SAM also allows for unidirectional workflow when coupling between the source and the platform is weak, or bidirectional workflow for higher coupling between the source and platform. As we approach the end of the presentation, I will highlight several key industries and associated electromagnetic devices. In aerospace and defense, common applications include installed antenna performance, as well as antenna element design, lightning strike on an aircraft, and radar cross-section. In transportation and mobility, antenna performance and placement are important, along with cable harness design, automotive radar for range finding and velocity, and of course, electric motors. In the energy market, components include high voltage devices, transformers, and motor or generator design. In industrial equipment, applications include RFID design, wireless connectivity on assembly line or warehouse, motors and actuators, and again, co-site interference for closely placed antennas. In life sciences, applications include MRI devices, wireless implants, wearable devices, as well as electron guns. And lastly, high tech, where wireless connectivity continues to be important for antenna performance, microwave and RF component design like this antenna with a matching network, EMI and EMC compatibility for FCC compliance, signal and power integrity for PCB design, and touchscreens, as well as cable networks and harnesses. Summary of benefits. Summary of benefits for CST Studio Suite. DC to daylight electromagnetic spectrum analysis with multiphysics capability. Advanced user interface with CAD and SOLIDWORKS integration. Enhanced innovation and understanding of the design space. Virtual prototyping allows for early awareness of design and compliance issues. Reduced time to market with cost savings. That brings us to the end of this presentation, and we can now address any of your questions.
Great. Thank you, Jim. So that hopefully everybody sees the in-depth richness that CST Studio Suite is bringing to the table. Like I said at the beginning, we just haven't had anything remotely close to this point, and I find this to be pretty exciting for those niche markets that require this. We will go ahead and look at some questions here. I did have one come across. I've had two come across, but I just want to highlight the fact that those solvers Jim just talked about were basically coupled in many ways, giving you, for an engineer that is looking for to solve a certain challenge, many times we have to do many types of studies to gain that full understanding of what the system's undertaking. And the tool sets that are built into this allow for that. We can go from one to the other and really get a lot of data points, so we can make some really good decisions moving forward. So they're all the solvers can be coupled. And Jim, if you have anything to add to that, go ahead.
Well, just to that slide where it talks about you can either have even unidirectional or bidirectional. And what that means is, when you have, when you're importing a field source from, let's say, an antenna, And if the structure that you're placing it on in the more larger analysis is actually affecting like the or affecting the impedance of that antenna or something else, it can then go back and resolve it. So that's called bidirectional solving. So yeah, all the solvers can be integrated together. Primarily, you integrate them when you're integrating different components, as well as antenna placement studies are a really big one.
What type of hardware requirements is there regarding this, Jim?
Well, there was that one slide that talked about the difference of time domain and frequency domain, and these are the really primary two approaches in electromagnetic. It's the two forms of electromagnetics. There's time domain equations and there's frequency domain equations, and they give you they approach the same model in different mathematical ways. But the time domain primarily benefits from GPUs. So it is written to take advantage of hardware acceleration and common GPUs today. The frequency domain does not utilize GPU. It utilizes increased number of cores on a CPU. So, my recommendation, a common platform would be just a dual CPU workstation with maybe minimum 16 cores per processor. So that'd give you a total of 32 solid cores for frequency domain. And then maybe purchase a hardware accelerator if you're doing models that are really, really large. Otherwise, you can get by. There is speed enhancement with cores also for time domain. It's just that the GPU is, it's like light speed. So, but also on top of all that, if you get the cloud licensing, you can do cloud computation. And so that's that way you don't have to purchase any of this hardware. You just kind of pay as you go and build your own virtual machine for whatever application that you're actually studying.
Excellent. Thank you. Regarding licensing, Jim, we have some questions surrounding term licensing versus perpetual versus that. Can you just speak to that for a moment? What the options are?
Absolutely. Just like most Dassault products, so you can either do quarter to annual leasing, which includes all the software updates during that period of time, as well as support, or you can have a perpetual license, and that way you have that indefinitely. And there's also cloud licensing, and we even have something called a universal front end where you get unlimited use of the front end and all the design modules, but then you pay as you go whenever you hit the solve button. So that's for people or companies that are not using it every day. It's one of those things where they would pick it up more and put it down after a design cycle and pick it back up. And that way it's more of a pay as you go system.
Awesome. So that flexibility is there, everybody, for those of you that may just have a project come up once or twice a year, to kind of get you over that hurdle.
Mm-hmm.
All right. Mackenzie, do we have any? Those are the three questions I had come across. Were there any more questions on our end?
I don't think so. You guys discussed the end user one that came through. Did you see that?
Yeah, so the end user in general might not be the SOLIDWORKS user. So what we're asking our SOLIDWORKS clients is to think about, hey, am I in a design team that's analyzing any kind of these electrical devices, antennas, components, printed circuit boards, et cetera? And if the answer is yes, then your design team would benefit from using CST. And so what we're asking our SOLIDWORKS engineers is to, hey, if this is something that looks familiar in your team, help us please make that introduction, and so we can talk to them a little bit more about electromagnetic simulation and how well that's integrated with SOLIDWORKS.
Excellent. Yeah, if you're a SOLIDWORKS, like I am, some of this was all news to me. I'm not exactly electromechanical genius like Jim here, but like I said, I think there's probably pockets in each of our companies that we could, kind of pull into this and get them the right information. Just let them know.
And the last thing I'll say on that, Rob, is to keep in mind that all that solving capability is the base package of CST. So they don't nickel and dime you. It's not like a different in the industry more times than not, it's different applications that you have to buy the software and pay the maintenance. Where CST is literally like, you know, five plus more programs built into one. And so it's really a type of institutional software package that a company can invest in and know that they have a very, very broad capability of solution and design capability within that tool. So either they're going into cable assemblies or going into PCBs or antennas and high frequency components or motor design. You know, it's all built in there. Plasma analysis. I mean, you know, if it's electromagnetic physics, it's in there. And then on top of that, it does come with multiphysics for thermal, CFD, and structural. So it's
a solution. It's a suite. It's a
really suite.
Is,
yeah, sure is.
Henry had a question here really quickly. He's looking for some optimization tools. So, you know, in SolidWorks, I know I can say, you know, change the width of a pocket or the thickness of a plate to meet a certain goal I'm after. Does that type of functionality exist in CST Suite as well, Jim?
Absolutely. So it comes built with optimization for every solver that's in there. So it has optimization built into it. And there's several different solvers, optimization schemes the user can choose from, as well as they can also bring in their own optimization scheme from either a Python script or a MATLAB integration.
Awesome.
Yeah.
Well, I think that wraps it up, everybody. It's we've gone the distance here, and Jim, I really appreciate your time and clarifying what this offers. And everybody on the call and that will watch this in the future, please feel free to reach out to TPM, you know, your local account rep, myself, whoever you interact with. And if this is something of interest, you know, we'd love to dig into it a little further with you and make sure that we get the right solution and application in your hands. So again, if no one has anything else, well, I think we'll wrap it up. Thank you, Jim. Thank you, Mackenzie.
Thank you so much.
Everybody have a great afternoon and stay safe in the weather.
All right. Thanks, Rob. Take care.